is a laptop desk, and this is a briefcase. Both of these incorporate some of the same joinery. The laptop desk is a box that's put together with finger joints, as is the briefcase. The bottom of the laptop desk rests in stopped grooves, as does the top and the bottom of the briefcase. The laptop desk, however, has what is called a breadboard lid. All of the joinery that I just mentioned, the breadboard joinery, the finger joints, and the stopped grooves, all of those are done not just to get the parts to hang together, but also to let the wood move. This is especially important in breadboard joinery. In most of the joints that you will do when you're building projects, the wood reinforces itself. You put one part against another, and the two have remained straight because they are stuck together that way. For example, if I were to take, here's two parts that I'm going to be cutting on a little later on today. If I would take this part and glue it to that part, it would keep this board straight, and this board would keep that board straight. If I put them together at the corner, which is what I'm going to be doing, the way they come together would prevent each board from cupping or warping. However, sometimes you just have to let a board hang out on the project without any adjoining parts that brace it. And that's what's happening here with the lid to this box. This is just a normal piece of wood, and if it weren't for the breadboard joinery, this probably would have expanded and contracted through a year's time and would have warped. Here on the walnut briefcase, the top and the bottom are held in the. Let me open this and I'll show you. The top and the bottom are held by the parts of the box. There, you can see how the box is actually split to make this briefcase, and the front, back, and sides of the top and the bottom of the box keep the top and the bottom of the briefcase from warping or twisting. Not so with the lid here. To keep this fairly flat, Drew and I had to put breadboard ends on this. I'll turn this and you can see the breadboard ends. These pieces of wood, the grain runs perpendicular to the lid itself, and this helps keep the lid from twisting or warping, and it remains flat, so when you put it down, it stays flat. Breadboard joinery was something that was come up with a long time ago. It was used a lot on tables to keep the tabletops from warping. The problem is that, of course, you have a piece of wood here which is fairly wide that is expanding and contracting across the grain this way, and you're restricting it with these breadboard ends, or it looks like you're restricting it with them, and that these have captured it. That's not true. These breadboard ends are not glued to the lid. They let the lid expand and contract, and to plan out this sort of joinery, you have to know quite a bit about wood and wood grain and the types of lumber that you're using. If you go and you look at the first three of the things that I've prepared for the blackboard, you'll see that these talk about different types of grain and different types of lumber. Plain sawn wood, which is the most common kind of wood, is cut across a board. If this were a big log, it just would have been sliced just like that across the diameter of the board. Tangent tangent to the annual rings. Plain sawn lumber is done tangentially. If this had been a quarter sawn board, it would have been cut parallel to these rays, which are coming out from the center of the wood, or radially to the annual rings. There is a big difference between quarter sawn, radially cut lumber, and plain sawn, tangentially cut lumber in the way that it expands and contracts. We all know that wood expands and contracts across the grain, but tangentially it expands and contracts on the whole twice as much as radially. The rule of thumb is that tangentially, a plain sawn board will expand and contract about 8% of the width across the grain. If you have a 12-inch wide board, it will expand and contract a quarter of an inch over the years as the relative humidity changes in most parts of the country. If you have a board that is quarter sawn radially, it expands and contracts only 4%, or about an eighth of an inch for every 12 inches. If you look at illustration number 1, you'll see that I have three types of grain there. I have the quarter sawn grain, of course, and then the plain or flat grain, but I also have another type of grain called rift grain. Rift grain, the annual rings go through it at an angle. Okay, quarter sawn wood, the annual rings go from the top to the bottom of the board, the two surfaces of the board, perpendicular to the width and parallel to the edges. In a tangential board, they sort of curve through the board from edge to edge. But in a rift sawn board, they go at a decided angle. Rift sawn lumber, you split the difference. The rule of thumb is that rift sawn will expand and contract about 6% of its dimension across the grain. Now, of course, all of this is dependent upon species. The different wood species expand and contract at different rates. As I said, the rule of thumb is 8% and 4% for tangential and radial. But if we had built this laptop out of white oak, I would get an expansion and contraction across the grain of 10% tangentially. If we had built it out of quarter sawn mahogany, I would get an expansion and contraction rate of 3% radially across the grain. That changes with species, and if you really want to get into this stuff, and sometimes you have to. Sometimes you just need to pick a wood for how stable it is, or you have to know about the instability of the wood that you're working with. If that's the case, I would really suggest you go out on the internet and download a free copy of the Wood Handbook. It's put out by the Forest Products Laboratory up in Madison, Wisconsin. It is an organization unlike no other on the planet. They actually take a look at wood and have been doing research on wood for the better part of a century on wood as an engineering material. A lot of good information in the Wood Handbook. Absolutely essential, actually. And they have put it in a PDF format that you can download right off their website. Just go to Google or Yahoo and plug in Forest Products Laboratory. Great resource. One of the many charts that you'll find in that book will be a chart of radial and tangential expansion and contraction. Now, there's one other thing that you need to know about the difference between plain sawn and quarter sawn and the way it moves. Remember I told you that if you looked at the edge of a radially cut board, so I think I have one right here. Yes. It's sycamore, so there really isn't much difference between the annual rings. But you could, if you could see this, you could see that. Well, here I'll just put a a straight edge, and I'll line it up with an annual ring. There we go. You can see it's at a slight angle, but it's almost straight up and down, or parallel to the edges of the board. This is going to be radial at this edge and this edge. It's going to be quarter sawn all the way through. But a tangential piece of wood, and I have one right here, this piece of poplar, the annual rings on the poplar curve through the wood from edge to edge. At this point, we have pure plain sawn lumber. But over here, as the rings begin to curve down, we get more and more into rift sawn. If this were on some of the plain sawn boards, it actually goes to quarter sawn at the very edges. Not only that, there's a difference in grain structure between the top and the bottom as you get closer to the center. There is, for example, more plain sawn wood on the top, the bark side of the lumber, than there is on the heart side. Because of these differences and this mix of grains in most plain sawn lumber expands and contracts at different rates on the top and the bottom. This is why plain sawn lumber tends to cup, and it cups opposite the annual rings, which gets us back to the need for breadboards. Okay. The breadboards are attached to the wood with simple slot mortise or groove in the edge of the breadboards, and a tenon on the end of the lid itself. When you put these two together, okay, this then keeps the breadboard then keeps the lid from cupping. The problem is, how do you allow for the expansion and contraction? Well, if you look at the underside of the lid, right here, 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 and here, are little tiny dowels, 3/16 of an inch dowels in the that go through. They go through the breadboard, stopping about 1/16 of an inch before going through the top, and they go all the way through the tenon in the lid. However, the dowels here in the center go through a hole that is the same size as the dowels. The dowels at the edges, in this case the back and front edges of the lid, go through slots. These dowels in the center are called fixed dowel joints. Those in the nearer the edges are called floating dowel joints. And I have made the slots through which these dowels go long enough to take care of the expected expansion and contraction. Remember, I told you this is cherry. I'm expecting 8%, a maximum of 8% expansion and contraction. That'll be about 3/16 of an inch. Okay? The dowels go through a slot that I made by drilling two 3/16 inch holes side by side, and then sort of wallowing out the drill bit back and forth to cut the sides into a slot. This will allow a total of 3/16 inches expansion and contraction. But by pegging this in the middle, putting my fixed dowel joint in the middle, it expands and contracts from the middle, so I only get 3/32 of an inch here. You can see this is a little proud right now. 3/32 of an inch expansion and contraction on this side, and 3/32 of an inch on the other side. If I had put the fixed dowel joints, let's say at the back edge, then I would have a full 3/16 of an inch coming towards you this way. I would see a lot of misalignment on the front edge, and I would have to make longer slots here for the floating dowels. So you've got to plan for these things. Now let me show you how I made the tenon and the slot mortise. Let's go over here to Mark 5. First of all, I'm working with some fairly small stuff. So I'm going to remove our normal insert and replace it with a zero clearance insert. Actually, this has been used once before. Let me raise the table. You can do it without the zero clearance insert. You just have to get the saw very close to one edge or the other to make sure your wood is supported. This way, however, is a little safer. The zero clearance insert is made out of hard plastic, and it can be cut by the saw blade. There we go. Okay, I'm going to have to move it just a little bit to line it up with the slot that's already in there. There we go. Now, because that slot isn't long enough for what I have to do, I'm going to turn on the saw and slowly lower the table. I will turn on the saw as soon as I have plugged it in. I don't know why you guys couldn't plug this in for me. Okay, I'm talking to the dogs. Okay, now I want this to be have about a ½ inch protrusion. So I'll show you a little trick. This is a ½ inch board right here. I'm going to put another board on top of it. Okay, lower this or raise this a little bit and spin the saw blade until, there we go, it's brushing right there. At that point, it is just a little deeper than a ½ inch. It's not going to matter exactly how deep it is, as I'll show you in a minute. We're going to use the same setup to cut both the tenon and the slot mortise. Now, let me bring this over here and set the fence exactly 1/8 of an inch, maybe just a little bit more, away from the saw blade. We're going to cut this groove by making 2 passes. We're going to pass the wood over the saw blade, then we're going to turn the wood around end for end and pass it over again. And the reason for that is that centers the groove here perfectly. Absolutely perfectly. We don't have to worry about getting the groove in the center of the wood. Now, in order to do the feeding, I'm going to use a fence straddler, and to help keep this thing aligned and against the fence as tight as possible, I'm going to use a feather board. And then I'm going to get the push stick because I don't want it to get lonely. All right, now let's make one cut here. We're somewhere here. There it is. There's the clicker. about as well as the dogs do. Okay, there you go. One perfectly centered slot in the middle of the edge of this particular breadboard. Now I'm going to get the lid here, and I need to remove. Let's see how wide that slot actually turned out to be. About 251, 252. Measured several places there. Yeah, about 252. So I'll need to move the fence so that it is 3/8 of an inch away from the saw. Now, I also could use, if I wanted to do this really, really accurately, I could get the dial indicator, put that in here, zero it out by bringing the fence all the way over to where it just barely touches the teeth. Attach the dial in zero here, and then move the fence 375 thousandths, or 3/8 of an inch, to my right, your left. There's 100 thousandths, 200 thousandths, 300 thousandths, and 75 right there. It turned out to be 376, but who's counting? Okay, let's, now, at this point, I'm going to introduce another little safety tool. If I were to cut this like that, it would do all right, okay? But it's fairly unstable here. It's top heavy and a little bit of actually a good stiff breeze, and this thing is going to tilt into the saw and either ruin the cut or get pinched and kicked back. So I'm going to trade this fence for another one. And actually, I'm not trading it all, I'm just trading it for a fence with an attachment on it. You would probably just put the attachment on. I'm doing this because of it takes less time. This is nothing more than a board that it's about 8 inches tall, and it's braced. I'll turn it towards you so you can see. It's braced on the back. There is a strip of wood, a plywood. It's all made out of plywood, cabinet grade plywood. The strip of plywood along the back keeps the face nice and straight. The braces help to keep it flat. It attaches to the 520 fence with Tenons. Put that back in. We can do the same thing. Let's get that dial indicator out. I'm just going to go for the 3/8 of an inch, measured off the tooth. Let's measure that again. Make sure it didn't move when I tightened it down, and it didn't. Okay. Put this against the fence. Check again with that. Looks like just for. I think I'm gonna widen this just a hair. At least for the first pass. Too much. Featherboard in place. Okay. note that I did not change the saw one iota. It's still at the same height, so that the length of the tenon that I just cut is going to be precisely the depth of the mortise that I cut. Now, I put these two together. Okay, they're a little tight. It's just a little tight, so I'm going to... Now, this is so close to fitting that I'm going to go back and get the dial indicator, and I'm just going to move this away. Let's see, I'm going to move it towards this saw about 3/1000. So I'll be shaving off 6/1000, and I'll be shaving off 7/1000 off the tenon. Now you'll notice that the same thing holds for the tenon as held for the groove, because I am cutting one side and then the other with the same setup. The tenon is perfectly centered in the board, as is the groove. That's a much better fit. There we go. Nicely done. Very little. In fact, by the time I glue that together, you won't be able to see that joint at all. That's, of course, I'm not going to glue together, am I? I've just spent all that time talking to you about making dowel joints. But nonetheless, by the time that this is all fitted, it will be all but invisible. They